Hey everybody, welcome to the third video in our series. This is the final video that you have to watch this week. And today we are finally getting to the greatest topic, the most quintessential chemistry topic, stoichiometry. Yes, this word that is right here. Yes, this word that is right here is pronounced stoichiometry. Oh, there's actually a joke. What's a chemist's favorite plant? A stoichiometry. You guys thought you were done with my bad chem jokes. You're not. Sorry. So let's go ahead and get into it. What is stoichiometry? Well, it is the study of mathematical relationships in a balanced chemical equation. So you guys remember that I've told you this whole year that everything that we're doing builds on itself. Well, this unit is the epitome of everything that we've been doing all year. It combines chemical reactions, our last unit, with the mole, with conversions. I mean, everything with sig figs, everything comes together in this unit. We can think of equations as recipes. When we started talking about chemical reactions, I sort of introduced you guys to this idea that in a reaction we have the ingredients or the reactants and the product, right? That's the thing that we make, that we produce. Well, we can think of these chemical reactions that we write as recipes. And when we balance those equations and add coefficients, those coefficients are like how much of each ingredient we need in order to make our final product. So if we use this idea of amounts of ingredients, instead of, 2 cups of flour, we need 2 NH3 molecules for whatever reason, we can use that idea to calculate and predict how much of a reactant is needed for a reaction. We can also predict how much product will be made in a reaction. So you can even think about it like you cannot bake cookies without, 2 eggs. But who decided that it was 2 eggs? Well, it depends on how many cookies you want to make. So if you know that you want to make 12 dozen cookies, right, you might need 3 or 4 eggs. So it's the same sort of idea, but with chemistry and with compounds. So we're going to predict and calculate how much reactant is needed for a reaction or how much product will be made in a reaction. So let's go back to this kitchen idea. In the kitchen, right, we do very simple stoichiometry whenever we make lunch. I made a grilled cheese, right? 2 slices of bread, 1 slice of cheese gives me 1 grilled cheese. In chemistry, it's the same recipe, guys. We've got 2 hydrogens, 1 oxygen, and it gives me, this time, 2 water molecules, right? But these coefficients, right, they just tell us how much of everything we need to make the reaction happen, to make the meal, to make the batch of cookies. Okay, so in chemistry, these numbers here, right, they don't just represent the amount of ingredients, because this is chemistry, of course, we want to make it a little bit more complicated. These numbers actually represent the number of moles of each substance. So we don't have 2 slices of bread, we have 2 moles of hydrogen atoms. We have 1 mole of oxygen atoms. Right? And we can produce in that reaction 2 moles of water molecules. So if I wanted to make 2 moles of water, I would need 2 moles of hydrogen and 1 mole of oxygen. But what if I wanted to make 4 moles of water? Well, we can think about that. If I wanted to make 4 moles of water, well, I would have to rebalance my reaction because now I have 4 oxygen atoms and I have 8 hydrogen atoms on the right side of this equation. So I would need to double everything. I would need 2 O2s. I would need 4 H2s. So I can use the base reaction that we have, right? We learned how to balance chemical reactions. I can use that base reaction and modify or predict what would happen if I made a change. So if I wanted to make 4 moles of water, I would need to change the amount of hydrogen and oxygen that I started with. Unlike class where we, mix things based on the reactions that I give you. I know exactly how much stuff you're going to make. There's no real question to it. That's not really how chemistry works in real life. In the real world, chemists perform reactions to make useful things, right? They're not just making something explode because I want to talk about explosions and because I like lighting things on fire. Right? In the real world, chemists use reactions to make medicine, right? To make products that we use, shampoo, conditioner, soap, Germex. I can't even go into so many things are made by chemists. And when we learned about chemical reactions, we learned about how to figure out what chemicals and conditions would be needed to make those reactions take place. But there's one thing that we didn't really talk about. The real world, things cost money. Things are expensive. We can make products, right? Like if I wanted to make magnesium oxide, right? And so I had some magnesium and I had some oxygen. I could put the magnesium in the fire. I could burn it and produce magnesium oxide. I could just mix a bunch of everything together, but we'll end up wasting a lot of reactant if we just guess at how much we need. Does that make sense? Let's talk about another example. Okay, let's go back to our grilled cheese. If we have 2 slices of bread and 1 cheese slice, we can make 1 grilled cheese. Now, it's fine. Your parents will go to the store. You can buy a loaf of bread. You can buy a package of sliced cheese. It doesn't matter that you aren't going to make the exact right number of sandwiches, right? Like a package of cheese maybe has 10 slices in it, and you can get, say, 12 sandwiches out of the bread. It doesn't matter if the amount of cheese won't be the exact amount of cheese needed to make an entire loaf's worth of sandwiches. But what if cheese costs $20 a slice? Well, things would be expensive, right? We would have to be more careful about buying exactly the right amount of cheese that we needed and exactly the right amount of bread that we need so we're not wasting any materials. And that's what stoichiometry is for. That's what these chemists are worrying about. They don't want to waste a lot of their ingredients. They want to make sure that they have just the right amount to be useful in a reaction and not waste anything, use everything to its max capacity. That's why stoichiometry is important to chemistry. But what do these calculations look like? I'm sure you guys are scared because stoichiometry is a huge word, but so is anti-disestablishmentarianism, right? It doesn't have to scare you. So let's talk about how to do these conversions. There's one thing that we need to talk about, mole ratios. A molar ratio or a mole ratio is a ratio, which means just an equality, of coefficients from a balanced chemical reaction that tell the relative amount of the substances that we have. So if we have in our reaction here, this is our water reaction, I just flipped the reactants and products around. We have a ratio of 2 water molecules for every 2 hydrogen molecules, or 2 water molecules for every 1 oxygen molecule. So that's our ratio from the balanced chemical reaction. That's the ratio of moles, right? 2 moles, 1 mole. But this only works if we have a balanced chemical reaction. That's why we had to learn about balancing before we could learn about stoichiometry. Now, if I, in an example, right, had 4 moles of water, right, like we talked about on the last slide, if I had 4 moles of water, I would need to increase the number of moles of both hydrogen and oxygen. Okay, I would have to keep the ratio the same. 2 to 2 is the same as 4 to 4. It's a 1 to 1 ratio. If I have 1 water, I have 1 hydrogen. But the ratio between the water and the oxygen is a little bit different. That's a 2 to 1 ratio. So let's look at what that looks like in math terms instead of me just talking. In this first example here, if I have 6.5 moles of water and I break that water molecule into its parts, so into hydrogen and into oxygen, I want to know, well, how many moles of hydrogen would be formed? So if I'm starting with 6.50 moles of water, I want to know how many moles of H2 can be produced. Let's set up our conversion. Moles of H2O is what I want to cancel out. Now you might think we're in the same units here. Sure, it's true that these are both in moles, but you'll notice that there's a label on here, right? I'm starting with, on the left, H2O, and on the right, I'm ending in H2. Those labels are very important because I can actually convert moles of H2O into moles of H2 using the ratios from this chemical reaction. I'll show you what I mean. How many moles of H2O are there for every mole of H2? Well, I can just take these numbers from the balanced chemical reaction. Those are the mole ratios. Just a ratio is another word for conversion factor, right? We learned that in August or September or whenever we learned it for the first time. These twos represent how many moles of each molecule I needed to make this reaction happen. So now when I solve, what I'm essentially doing is converting moles of H2O, those units cancel out, into moles of H2. Then I just need to solve. Luckily for us, if we do 6.5 times 2 and then divide that by 2, those 2's are going to cancel out. That's a nifty little math trick for us. So we are going to end up with 6.50 moles of H2. That's how many moles of hydrogen can be formed if I start with 6.5 moles of water. Because if you look at our reaction up here, right, 2 moles to 2 moles. It's the same number. So however much water I start with is how much hydrogen I can end with. That's not the case for oxygen. It says using the same reaction, how many moles of oxygen could be formed? Well, assuming that I'm starting with that same 6.50 moles of H2O, let's try converting that to moles of oxygen. So I'm going to set up my conversion. Moles of H2O goes on the bottom, and moles of O2 goes on the top. Now I get these numbers from the balanced chemical reaction. The balanced chemical reaction shows 2 moles of water for every 1 mole of oxygen. So now when I solve this, what I'm actually doing is taking that 6.5, multiplying by 1, and then dividing by 2. So I can only produce 3.25 moles of oxygen when I could produce 6.5 moles of hydrogen. Well, that makes sense, right? If I have 4 slices of bread, but only 1 slice of cheese, how many sandwiches can I make? I can still only make 1 sandwich because you have to keep the ratios the same. I want you to go ahead and get out your top 10 handout with the mole conversions that we were using last time. In the last couple of videos, we only looked at the front. Now I want to look at the back. This stoichiometry concept map shows how everything plays together. The front side of this top 10 handout is just one side. It's half of this. We can go from volume of a gas to moles. We can go from grams to moles. We can go from particles to moles. We can go from volume of a liquid to moles, right? That's what's on the front side. It looks, like this though, with moles in the middle. But I've just upped our game because the front side is only dealing with one substance. So only one thing, like moles of A. Maybe A is water. So I can only convert using water molecules. But with stoichiometry, I can get from one substance into another substance. And that's by using the coefficients to set up a molar ratio, where we convert between moles of A and moles of B. And then once I'm on the other side of this map, right now everything over here is just like it was on the front side. Moles to volume, moles to particles, moles to grams. But I've got this extra step in the middle that allows me to change substances. Right? If you're changing the substance, then you have to use that mole ratio. And you have to use the mole ratio if you want to change or convert between substances. Let's go ahead and work through some examples. I have this reaction here at the top that says 2C4H10, so that's 2 moles of butane plus 13 moles of oxygen can react together to form 8 moles of carbon dioxide and 10 moles of water. You guys remember when we had to balance this one in class? You guys were all really pissed off at me working on your whiteboards, and you're like, I can't figure it out. And then 1 or 2 people figured it out, and I was like, oh, you just double the water. Anyway, I missed you guys. Question 1. If 12 moles of oxygen react, how many moles of carbon dioxide are formed? Okay, let's look at the reaction. In the reaction, I'm starting with 13 moles of oxygen. And it says 13 moles of oxygen will produce 8 moles of carbon dioxide. But then in the question, it says, what if I only have 12 moles? That means I have a less starting material. So if I'm starting with less, it makes sense that I won't be able to produce 8 entire moles of carbon dioxide. I'm expecting to get a number slightly smaller than 8 because I have less oxygen when I start. Let's see if we can do this problem, and we'll see if that works out for us. So let's say I'm starting with 12.0 moles of O2. Now on my top 10 handout, it says that if I ever want to convert between substances, which I do, in this case I want to convert to moles of CO2, if I want to convert between 2 different things, I have to use a molar ratio. That's where I'm going to have moles of one thing on the bottom. In this case, it's moles of O2, because that's what I want to cancel out. And then moles of CO2 on the top, because that's what I want to convert to. Now, I get these numbers whenever I have moles and moles. I have to use a balanced chemical reaction. And this reaction says that every time I have 13 moles of oxygen, I produce 8 moles of carbon dioxide. That's the molar ratio. Now let's see if we get fewer than 8 moles when we multiply this all out. You take the 12 moles, multiply by 8, then divide by 13. And you get 7.38 moles of CO2, okay? Which is slightly less than 8. So we were correct. Of course, we can't produce 8 whole moles of carbon dioxide. I didn't start with as much oxygen as I said. Let's take it the other direction. What if I know not how much I'm starting with, but what if I want to make 13.5 moles of water? What if I want to make 5 grilled cheese sandwiches? If I want to make 5 grilled cheese sandwiches, I know that I need 5 pieces of cheese and 10 slices of bread. Well, let's do the same thing, but with chemistry. If I want to make 13.5 moles of water, how much of my initial ingredients will I need? This is 2 separate problems. Let's start with the C4H10. I want to convert moles of water to moles of butane. So I'm going to set up a conversion. Moles of water goes on the bottom. Moles of butane goes on the top. And then I just include my molar ratios. In the reaction, the number that is associated with moles of water is 10. Okay, so in my reaction, I only made 10 water molecules. This time I want to make 13.5, which means I'm probably going to need more than the 2 moles of butane that the reaction says. I'm going to need 2.7 moles of C4H10, not just 2. With sig figs, there would be a 0 there. Okay. So these molar ratios are helping me to predict how much of my reactants I need. That way I don't have to waste anything. I don't want to just, throw in 5 moles of butane just because I know that'll work. That would be wasting 2.3 moles. I want to use exactly 2.7 if I can. If I want to know how much oxygen I'm going to need, 13.5 moles of water, I'm going to have to set up another conversion, starting with the moles of water on the left, and I want to convert to moles of oxygen. So on the bottom, I'm going to put moles of water. On the top, moles of O2. And again, I'm just going to use my molar ratios from the chemical equation that says for every 10 moles of water, I would need 13 moles of O2. Again, we're expecting to get an answer that's higher than 13. My reaction says that it takes 13 moles of oxygen to make 10 moles of water, but I want to make 13.5 moles of water, so I'm going to need more oxygen. So when I solve this, it turns out I'm actually going to need 17.6 moles of oxygen in order to make 13.5 moles of water. If you have questions on this topic, remember that you can email me or pause the video, go back, watch the whole thing again. I'm just going to keep moving forward with examples. All right, let's add in another step. In this question, I want to know how many moles of NH3 can be formed if I have 2.59 grams of H2 reacting with excess N2. Excess just means I have extra, so I'm going to have some leftover N2. I don't really have to worry about it right now because it's just going to be left over. Like if I have 3 slices of bread, I don't want to use the butt of the bread anyway, so this is okay. This is good excess. Now, I'm going to go ahead and try to set this reaction up. I know that I'm going to start with 2.59 grams of H2. Making sure that you include this label here is very important when doing stoichiometry, because we might have to convert between substances. So if I have 2.59 grams of H2 when I start, I want to know how many moles of NH3 I'm going to end up with. Again, make sure that you have that label there, that NH3. Now let's look at our mole map or our stoich map. I'm going to probably just call it the mole map. We need to look at this mole map to help plan out how we're going to get from grams of H2 to moles of NH3. Since we switched substances, we can say H2 is, substance A, NH3 is substance B. It doesn't really matter which one is which, but we're starting in grams of one thing, and we want to get to moles of the other thing. So we're going to have to do a couple steps here. First, we're going to have to convert grams of A into moles of A. Then I can convert moles of A into moles of B. You can only change substances with a molar ratio. Okay? You cannot go straight from grams of A to moles of NH3. It doesn't work like that. You can only change substances with a molar ratio. If I said it multiple times, that means you should probably write it down. Okay? Bold it, star it, circle it, do whatever you have to do. You have to have a molar ratio if you want to change between two substances. Okay, I think you've probably got it. Let's see if we can set up this conversion skeleton. If I'm starting in grams of A, I need to first convert that to moles of A. So I'm going to cancel out of grams of H2. I want to go to moles of H2. Then I can set up a second conversion that takes me from moles of A into moles of B. So moles of A is moles of H2, B, that's moles of NH3. So I have my skeleton structure here. Now I need to fill in my conversion factors. The mole map tells you what the conversion factors are going to be. In order to get from grams to moles, we have to use the molar mass, which means I have to calculate the molar mass. Luckily, hydrogen is an easy one. H2 So you take the molar mass of one hydrogen, 1.01, multiply it by 2. So the molar mass of H2 is 2.02. And that's how many grams there are for every 1 mole. Remember that molar mass, there's always a 1 by the moles. All right, when we look at the next conversion, it says I need a balanced chemical equation. Do I have a balanced chemical equation? Shoot, sounds like I'm going to have to write one. This is going to be back to our how do we write the reaction. We have to figure out what are the reactants here and what are the products. It says how many moles of NH3 are formed if H2 reacts with N2. So when I see the H2 reacting with N2, that screams reactants to me, which means that the NH3 has to be the product. So let's see if we can write this reaction. I have H2, some amount, and I'm combining it with N2, and I'm going to produce NH3. Okay, so I have my reaction. The problem is that this reaction has to be balanced. Now, if you are still struggling a little bit with balancing, that's okay. I highly recommend that you do the balancing practice that's in the chemical reactions extra practice worksheet that I posted on Classroom. That's one of those worksheets that you can do for review. But hopefully you're okay with balancing by now. I can see on the left I have 2 nitrogens. So on the right, I'm going to need 2 nitrogens. So I'm going to have to put a 2 here in front of NH3. So that gives me 2 nitrogens, but it also gives me 6 hydrogens. So now I need to find a way to get 6 hydrogens on the left. All I have to do is add a 3 in front of H2, and now my reaction is balanced. And now that I have a balanced reaction, I can go back and I can fill in this mole ratio. So how many moles of H2? It says there's a 3 there. So 3 moles of H2 can make 2 moles of NH3. So now I have this whole reaction written up. I just need to solve it. So we multiply across the top and we divide by everything that's in the bottom. When you do that, you get 0.855 moles of NH3. And that's my final answer. I just converted from grams of one substance to moles of another substance. Now let's try another one. I'm going to erase my mole map here so that we can use it again. Let's try this next example. So in this next example, it says how many grams of N2 are needed to react with all 2.14 liters of H2 when they react to form NH3 at STP. So it seems like I'm dealing with the same reaction from before. So make sure that you have that balanced chemical reaction written down. It's going to be the same reaction here in question 4. This time though, I'm starting with 2.14 liters of hydrogen. And I want to convert that into grams of N2. So let's look at our mole map, figure out how we're going to set this up. In liters of one thing, so I have liters of a gas, H2 is a gas, so I'm down here in volume of A, and I want to convert into grams of a second thing. So I want to get to grams of B. So first I need to go from volume of A to moles of A, then from moles of A to moles of B, then from moles of B to grams of B. So we're going all the way through this mole map right now. So let's see if we can set this up. Starting in liters of hydrogen, I want to convert from liters of hydrogen, so liters of H2, into moles of H2. That was my first step. Then I want to get from moles of H2 to moles of B, so moles of N2. So put moles of H2 on the bottom and moles of N2 on the top. Then I want to convert from moles of N2 into grams of N2. So I just followed my mole map here. First I went from volume to moles, then moles to moles, then moles to grams. That's my setup. Now I just need to fill in all of the information. So on that first step, when I went from volume to moles, I need to use 22.4 liters equals 1 mole. This is something that we talked about in the first video. This is Avogadro's other hypothesis. We're going to put the 22.4 with the liters, and that's for every 1 mole of H2. Then, to go from moles of one thing to moles of another, I need to use my balanced chemical equation. So let's look back up at the last problem. There are 3 moles of H2 to react with 1 mole of N2. Remember, if there's nothing written there, it's an implied 1. Just like in algebra, we don't have to write 1x, we can just write x. So there's 3 moles of hydrogen for every 1 mole of nitrogen. Now, to get from moles of B or moles of nitrogen into grams of nitrogen, I'm going to have to use molar mass. So you take the mass of 1 nitrogen, which is 14.01, you multiply it by 2, so 28.02 grams of nitrogen for every 1 mole of nitrogen. When we solve, we get 0.892 grams of N2. That's how much nitrogen is needed to react with 2.14 liters of hydrogen. That's how we use the mole map. Let's keep doing some more examples, see if we need any more help. This is how many liters of N2 are needed to make 34.6 grams of ammonia, NH3, STP. So again, it seems like I'm using the same reaction from before, so I'm just going to go ahead and rewrite it. It was 3 moles of NH2 plus 1 mole of N2 created 2 moles of NH3. So since I'm using the same reaction, I just rewrote it here. But let's go ahead and think through everything here. I'm starting with the 34.6 grams of NH3. And I want to convert that into liters of N2. So let's go ahead and look at our mole map. Let's see where we need to go here. I'm starting in grams of A. I want to end up in liters of a gas, right? N2 is a gas. I want to end up in liters of B. We're going to start in grams. We're going to go to moles. Once we're in moles, we're going to switch substances, go to moles of something different, then moles down to liters. Let's set up this skeleton here. I'm starting in grams of NH3. I need to convert that into moles of NH3. Then once I'm in the moles of NH3, I'm going to use my balanced chemical equation to get to moles of N2. Once I'm in moles of N2, I can convert to liters of N2. There's my skeleton. Now we need to fill in all of the information. To go from grams to moles, you have to use molar mass. Calculate molar mass, it's 14.01, the mass of nitrogen, plus 1.01 times 3, so total you get 17.04. And that's how many grams of NH3 are in 1 mole of NH3. Then once I'm in moles of A, to get to moles of B, I need to use my balanced chemical equation, my molar ratio. It's 2 moles of NH3 for every 1 mole of N2. Now from moles to liters, I need to use that 20.4. So that's how many liters are in 1 mole. Got everything set up. Now I just need to calculate. And when you do that whole calculation, you should end up with 22.7 liters of nitrogen. All right, guys, let's see you try. I want you to go ahead and try to pause this video, write this equation down in your notes, and see how much of this you can do on your own using your mole map, of course. There's already a balanced chemical equation for you. We just need to see if you can put those conversions to the test. So try it, and then unpause the video, and then you can compare your work to my work. All right, hopefully you got at least this far with your setup using that mole map. All right, check your setup with me, pause the video again, and then you try to fill in all those conversion factors. All right, so this is the full conversion setup here with all of my conversion factors filled in. The only thing I have left to do is solve. I end up with 31.8 grams of tin 4 fluoride that can be made from the original 12.8 grams of hydrofluoric acid. Let's try another one. All right, this one looks like it's got a couple different steps for us. So it says the decomposition of solid potassium chlorate allows oxygen gas and potassium chloride to be made in labs. All right, you've got all the questions here. This is going to have you do everything. You're going to have to write the reaction from what's given to you, then balance it, and then do a couple of conversions. I highly encourage you to pause the video and try to do this on your own. I'm going to do each question one at a time. So if you pause the video and play it again, I'm going to have A done, then I'm going to have B done, then I'm going to have C done. But I encourage you to try to do the whole thing on your own before checking your work. All right, so there's your balanced chemical reaction. Now let's see if you can do B that says if 5.150 grams of potassium chlorate decomposes, what volume of oxygen gas would be obtained at STP? So again, go ahead and pause the video, try to do that calculation. All right, so when you calculate everything out, it turns out we can make 1.412 liters of oxygen gas. All right, I got one more question for you. It says how many grams of other product will be made? So that other product would be potassium chloride. Go ahead and pause the video, see if you can do this calculation. All right, when you calculate all of this out, you should be able to make 133 with sig figs grams of potassium chloride. I hope this video served as a good introduction into stoichiometry for you. I'll remind you that you can rewatch this video as needed, but really I highly recommend relying on your mole map and just working through those example problems that I posted as a worksheet. So remember that you need to complete that worksheet and upload pictures of it to Google Classroom by the deadline. You should be able to get credit for it. Again, email me if you have any questions at all about stoichiometry, about mole conversions, about molarity, about the Avogadro's other hypothesis with molar volume of gases. Like, email me, reach out, let me know if you need anything. See you next time, guys.